Hello, George Nodzik here. Sunday, September 29th, 2019. In this video, I'm going to be talking about ellipses. I've talked about ellipses in my first video called Flat Earth Answers and Explanations. I recommend you go to that video. In the first half hour, I discussed ellipses with respect to celestial mechanics, like the Earth orbiting the Sun. In this video, I'm going to be talking about ellipses that would be more relevant to describing the surface of the Earth. There's a couple of ways we can represent ellipses. One is we have an ellipse centered with respect to the XY axes. The longest axis of the ellipse is called its major axis. The shorter axis is called the minor axis. And the halfway from the center on out on the major axis is called the semi-major axis, and halfway on the minor axis is the semi-minor axis. The length of the semi-major axis is A. The length of the semi-minor axis is B. Now, we can represent an ellipse in Cartesian coordinates where we have an XY axis in the following manner. That x over a squared plus y over b squared is equal to 1. I will derive that in another video from first principles where we're given the geometric definition of an ellipse, and this can be derived. It's not real easy to do, but it can be derived from first principles, but I'm not going to discuss it at this time. Now, another way we can represent an ellipse is through polar coordinates. That is, instead of picking a point on the x-axis and a y-axis, see, a point on the ellipse could be represented by going so far in the x direction and so far up in the y direction. This is called Cartesian or rectangular coordinates. Another way we could specify it is by a radial length from the center out to the point and the angle that that radial vector makes to the point from the center, some angle phi. In this case, the representation is r as a function of phi would be b over the square root of 1 minus e cosine phi squared, where e is called the eccentricity. E squared is 1 minus b over a squared. The eccentricity describes the flattening or the oblonging of the ellipse. If we're talking about a circle is a very special ellipse. It's a special case where the eccentricity is 0. The eccentricity becomes 0 when b and a are equal. That is, when the semi-major and the semi-minor axes have the same length, we are describing a circle. It is, in this case, the semi-major axis has length a, the semi-minor axis also has length a. So in that case, if b is equal to a, we end up with x squared over a squared plus y over a squared is equal to 1, or we multiply through by a squared, we have x squared plus y squared equals a squared. That's the equation of a circle. So the eccentricity for a circle is 0. A circle is a very special case of a general ellipse. Now, how can we get that from this? I'll show you that now. We start with this general equation for the ellipse. And let's multiply through by by b squared. So if we multiply through by b squared, we are going to end, or ab squared, I mean, ab squared. So if we multiply through by ab squared, we have b x squared, whoops, b times x squared plus a times y squared equals ab squared. I've multiplied through by ab squared. If we have ab squared, the a squareds cancel, we end up with b squared. Same thing here, ab squared, the b squareds cancel, we have a squared. So, we have that. But we also know that by Pythagoras' theorem, that the radial distance out from the center is the square root of x squared plus y squared, or we can write r squared is equal to x squared plus y squared. Okay, by Pythagoras' theorem. Now let's multiply through by a squared. So we have a r squared equals a x squared plus a y squared. Multiplied through by a squared in that equation. Now let's substitute for ay squared into this equation. So we end up with bx squared plus ay squared then would be a r squared minus ax squared equals ab squared. Now we can combine our x's, so this becomes b squared minus a squared times x squared plus ar squared is equal to ab squared. Now let's look at the equation for eccentricity. Let's multiply through, or I'm sorry, that's squared. Let's multiply through by a squared. So this is a squared equals a squared minus b squared. Well, b squared minus a squared is the negative of this. So b squared minus a squared equals minus ae squared. Let's put in for b squared minus a squared. So putting in, this becomes minus ae squared x squared plus ar squared equals ab squared. Now, we see we have an a squared in each term. We can get rid of that, so we end up with minus e squared x squared. We're going to factor out, divide out the a squared out of each term. Now, let's solve solve here for r squared. But before we do that, we need to get rid of our x. Well, we know from Pythagoras' theorem, remember, r is our radial distance out. This is x, this is y, and this is theta. Well, x is equal to r cosine, or phi. R cosine phi, using trig functions. So we put in for x squared. X squared would be r squared cosine squared. So we end up with minus e squared r squared cosine squared phi plus r squared equals b squared. Now we have an r squared in these two terms on the left, so we can combine those. So we will now go and combine them. Let's put it Let's see here. Let's write this equation that we start out with as x over a squared plus y over b squared equals 1. So we can get rid of that here. And what we're looking for is to derive this equation. And we're almost there. If we combine the r squareds, we have r squared times 1 minus e squared cosine squared phi is equal to b squared. We take the square root of both sides, so we got r times 1 minus e squared cosine squared phi to the 1/2 is equal to b. We're solving for r is b over the square root of 1 minus, we can combine these two as e cosine phi quantity squared, which is this equation here. So we verified that that equation is indeed correct. That's a polar representation for the ellipse. So I'm going to write this here. Is r is a function of phi is b over the square root of 1 minus e times the cosine of phi squared. All right, now that's our main equation. This is relative to the center of the ellipse, a representation. We also could represent the polar coordinates relative to a focus. And this is more applicable to celestial or space mechanics because planets and satellites orbit about a central mass where the central mass is at the focus of the ellipse. This is one of Kepler's law. Kepler's first law is that states that all orbits are ellipses with the sun at a focus, or the major body at the focus. I'll talk about this later. We're not going to talk about this particular case right now because I'm leading up to getting to representing the Earth, the surface of the Earth, in terms of an ellipse or an ellipsoid. And it's more natural to describe the coordinates relative to the center of the Earth rather than at a focus, because there's nothing orbiting. We're just talking about a description of the surface of the Earth. So we'll talk about this another time. So this is what we're focusing on now, is that we want to have the ellipse described relative to the center. And this is just an expanded view of 1/4 section, or the 1 quadrant. An ellipse is symmetric about both axes. You could flip this side over and it'll match this side. We could flip up and down and they will match. So each quadrant has the same description. We have symmetry about both axes. So we only need to consider 1 quadrant when looking at the properties of the ellipses. Now, so what we have here now is our polar coordinate equation for the ellipse relative to the center of the ellipse. Now, another important aspect that we need is to get a description of the tangent line, or a tangent to the surface of the ellipse. And the tangent is a line that just touches at one point the surface of the ellipse. The equation for the tangent is that y is equal to b squared over y1 minus x1 over y1 times b over a squared x. This is the equation of a line. Y equals y0 minus mx. Now the point x1, y1 is where the tangent is touching the ellipse. That's the point of intersection of the tangent with the surface of the ellipse is x1, y1, and this b squared over y1 is what we call the y-intercept, that if we were to extend the tangent line, it would intercept the y-axis at point y0. And then this portion is the slope of the line, x1 over y1 times b over a squared. That's our m. This is m, this is y0. This is important for when we're sighting along the surface of the earth to compute drop distances. We need to know the tangent line that's touching the surface of the ellipse, and that's given by this. Because ultimately what we're going to be doing is, if we have, say, the elliptical surface, and then we have a tangent line to that surface, say this is the tangent, and it intersects in point x1, y1, at that point, that would be our point of observation. Then, relative to the surface center, if we go out a distance, say to our target, we have a target sitting there, then we draw a radial vector out. The drop distance then will be the perpendicular distance from the tangent line to the surface. This would be, let's call it delta y. That's our drop distance. Now, when we have a perfect sphere or a perfect circle that describes the surface of the earth, then delta y, as we all know, is 8 inches per mile squared, where s is the arc distance along the surface. And that gives us our drop distance. We take the distance out from the observer to the target, square it in miles, take that distance in miles, square it, multiply by 8 inches, and then that gives us our drop distance. Well, I got to thinking about, how about the real case where we don't have a perfect sphere for the earth? Does that impact the curve calculators? All curve calculators on the internet are based on a perfect sphere. So one has to ask the question, are they in error or not when you take into consideration the fact that the surface of the earth is an ellipse of revolution? It's an ellipsoid. So that's what the video that will follow this one will discuss and investigate to see how good the earth calculators based on a sphere agree or doesn't, whether it agrees or does not with the ellipsoid, and if it doesn't agree, then how much is the error? And that's where we're headed on this. So we can define the general ellipse implicitly in this fashion: ax squared plus bxy plus cx squared is equal to 1. Now, when the ellipse is moved off the axis, its center is moved off the axis, you end up getting these cross product terms. The fact that we had the equation of the ellipse being x over a squared plus y over b squared equals 1 means that we have the center of the ellipse on the origin of the xy axis, so we don't end up with cross product terms. Now, for the general ellipse like this, the area of the ellipse is 2 pi over the square root of 4ac minus b squared. So for the ellipse, 4ac has to be greater than b squared for this to be a real number. If 4ac was less than b squared, this would be imaginary and we wouldn't have the area. So this is a condition for the ellipse, that in a general equation like this, 4ac minus b squared has to be greater than 0 to be defining an ellipse. And this also can be written in this fashion as pi a squared times 1 minus e squared, where e is the eccentricity of the ellipse. Now, 1 minus e squared, if we look at our equation for eccentricity, 1 minus e squared would be b over a squared. And if we put that in here, we get pi a squared times the square root of b over a squared. And we take the square root of that, this becomes pi a b for the area. So for the general area of the ellipse, we can write it as pi times the product of the semi-major axis and the length of the semi-minor axis, b. So that's the area for an ellipse. Now, we also have some important parameters called the curvature and the radius of curvature for an ellipse. Now, the curvature at a point xy, this is a mathematical geometric definition. The curvature at xy is kappa. We use the Greek symbol kappa, and this is 1 over a squared b squared times x squared over a to the 4th plus y squared over b to the 4th to the minus 3/2 power. That's called the curvature. Now, related to this curvature is what we call the radius of curvature. I'll describe that in a moment for you. So radius of curvature at point xy is given by rho. We use that to designate radius of curvature, and this for the ellipse is a squared b squared times x squared over a to the 4th plus y squared over b to the 4th to the 3/2 power. Now, let's look at the radius of curvature at the vertices here. The vertex along the semi-major axis is here at A, which would be the equator. This is at point x is plus minus a. We could be here or here, and y is 0. So in this equation, when y is 0, this disappears, and we have x squared over a to the 4th to the 3/2 power. So this becomes a squared b squared x to the 3rd over a to the 6th, or b squared x cubed over a to the 4th power. Well, x is equal to a at this point, so we have a cubed over a to the 4th, so this becomes b squared over a. So that's the radius of curvature at the equator. And up at the covertice, when we have x is equal to 0 and we have plus minus b, for the y, when x goes to 0, this now becomes a squared b squared. X is 0, so we have y to the third over b to the 6th power, and y is equal to b, so b third times b squared is b to the 5th divided by b to the 6th, so this becomes a squared over b. So it's just inverted. At the equator we have b squared over a, and at the covertice we have a squared over b. Now what radius of curvature is if you have a curve, say like this, the radius of curvature is at any point on the curve you can describe over a small length the best fit circle at some radius to fit that curve. And this is the radius of curvature at that point. At this point, the radius of curvature is much more gradual, so the radius of curvature at this point will be greater than the radius of curvature at that point, and so on. If the curve, say, came around and did that, then the radius of curvature at this point will be centered there. So at every point along a curve, the radius of curvature changes and the center for the radius of the curvature changes. So that's why we have different radiuses of radii of curvature along the ellipse. And it's because the best fit circle at any given point changes. So that's what we mean by radius of curvature. Now, one last important thing is the perimeter, or the distance along the curve. Now for the perimeter of the ellipse, let's call it C. This is the perimeter, and this is 4a times E, cap E of E, where little e is the eccentricity, and cap E is called the elliptic integral of the second kind. This is cap E here. This cannot be integrated out in closed form. It's a tabulated function called the complete elliptic integral of the second kind. The complete elliptic integral of the first kind is when the square root is in the denominator. So this is a complete elliptic integral of the second kind, and it's a tabulated function. It's a very famous, it pops up a lot of times, like for pendulum swings, timing of a pendulum in general. You have to use this tabulated function to get what the circumference is. There's no nice form for circumference like there is for area. Area is pi AB, very nice, but there's no nice closed form solution for the perimeter of an ellipse. Now, there's a really good approximation. Srinivasa Ramanujan came up with this, an Indian, and the perimeter is approximately equal to pi a plus b times 1 plus 3h over 10 plus the square root of 4 minus 3h, where h is defined as a minus b over a plus b squared. How we came up with that is beyond me, but it's a very, very good approximation for the perimeter of an ellipse. So that's what we'll end it there, that's all we'll need for figuring out the drop distance in general on an ellipse, and so that we can compare it with a drop distance on a perfect sphere. And I'll be discussing that in another video.